Hello, hello, Mohammed. All right. Oh, it was good to see you. Okay. And Vicky, good to see you dimensionally. And Gabriel, good to see you. And Aminata, good to see you. And Victoria, good to see your avatar. And
Good
Joel.
afternoon,
Oh,
Professor.
good afternoon. Thank you for the good afternoon. All right. Good to hear you. Uh, and good afternoon, Joel. And here comes. So good afternoon, Vicky, for the double. Good afternoon, Raina. Good afternoon, Sonam. Good afternoon, Joel, for the double. Good afternoon, Roger. Good afternoon, Gabriel, for the double. Good afternoon, Victoria, for the double. Good afternoon, Caitlin, for the double because of exclamation points and smiley faces, which just totally change everything. Good morning, Aminata, with the exclamation points and the three exclamation, and also a good morning. And the double, I think. Yes, sorry, blocking the. Okay. And Zoe, good afternoon with the. Ooh, that is so cute. Okay. Am I allowed to say cute in a physics class? I mean cat, not okay. And good afternoon. Okay. And good afternoon, Melanie. And hello, Anthony, with the picture. All right. Now and not even an iPhone. All right. Awesome. Awesome. It's good to know who you look like. Anyway. Okay. Okay. Hello. Yes. Hello, everybody. Good afternoon. Oh, what just happened? Okay. Sorry. Hold on. Something just pardon me for a minute. Bridget, hello, hello. I think that's Bridget, but my screen just went. Okay, give me a second. Sorry, sorry. Uh, Bear with me. Happening, happening. Second. Okay, more people coming. I'll be right there. Uh, ah, Sorry, coming. I know there's someone in the waiting room. There's all these things happening, and the thing's not. Give me 1 second. Sorry. Okay. Okay. Oh no. Once I'm sorry. Oh yeah. No. Okay. 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 Hold on. There's two people in the waiting room. Okay. Okay. I think we're good. Oh, chat. Oh, good afternoon, Bridget. Oh, I said, okay, that's good. Okay. Okay. I think we're good to go. Um, yes. All right. So let's get straight. We're continuing. We are good afternoon. No, no, no worry. Good afternoon. Good afternoon. Direct chat people. No worries. I haven't even, I'm apparently mentally late also. Okay. What we're doing today is using Gauss's law. I believe, yes, yesterday or Monday, like I screamed and yelled about the meaning of Gauss's law. like in principle, we took one example of flux calculation, found the flux in one sort of very particular example, found how surprisingly simple the flux result was. And then we said to ourselves, wait, but actually, the example was simple enough to reveal this truth about flux, but did this truth about flux rely on the simplicity of the example? And we found that even if we went to really complicated cases, that result would still apply. So we concluded this big law, which is the first equation written on the board right here. We are saying from now on, and I'm not, obviously I don't want to like repeat the whole lesson, but we are saying from now on that if you have any closed surface at all, the total amount, or the net amount of electrostatic flux emerging through that closed surface, emerging out of that closed surface, the net amount of electrostatic flux is fully determined by the total amount of charge enclosed by that surface, the amount of charge within. I'm going to say it a couple of different ways, and then today the whole point is to like apply that law to see how it's actually useful. Okay, i.e., homework 7. So that's what I'm going to turn to in a minute. But let me just see if I can say this one other way. The ultimate thing to flux is field through area. What that really means, field strength through area, what that really means is number of lines, of field lines passing through an area. So and remember, this all assumes that like whenever you're drawing a field line diagram, you're beginning with a scaling factor in your mind. Like any field line, like field lines are everywhere. But once we draw a diagram to depict a situation, we're drawing a representative sample of lines, right? And we begin by making a scaling factor decision in our minds or in the computer software or whatever. So we say something like, okay, for every 1 coulomb of positive source charge, we're going to draw 8 lines or something. So then from then on in, 8 lines represents 1 coulomb of positive source charge, which in turn means that then on in, 8 lines, 8 field lines in a drawing, in a diagram, represents a certain amount of newtons per coulomb of force waiting to happen in that space, right? So in other words, again, just to remind you that these field line drawings, they're not just sketches of a general idea. They are actually trying to communicate something precise and numerical. So when we talk about number of lines or something, the number of lines means something as long as everything's been drawn to scale. So at the end of the day, flux means amount of field strength through an area, but field strength is depicted by number of lines per unit area. That is to say, with field lines, the closer the lines are together, the more dense the lines are in a picture, the stronger the field is. Strength of field is number of lines per unit area, and flux means strength times area. So what flux really means, as abstract as all of this is maybe getting, when we talk about flux at the end of the day, what we're just talking about is number of lines. Which is, by the way, again, another reason we actually care about flux is that, in fact, as obscure and abstract as it may sound, once you're looking at pictures, once you buy into the pictures, flux is the easiest thing to see. Flux is just how many lines there are in a part of a picture. So what we're saying here is, what Gauss's law is saying is that if you picture any container anywhere in space, any closed surface, the total number of field lines coming out of that container is fully determined by the amount of charge found within the container. Because what we're really saying is field lines never start or stop except at charge points. Okay, so you'll know you're getting what I'm saying as abstract as the math might look, you'll know you're getting what I'm saying if it starts to seem stupid to you. I mean, it's not really stupid, but we are really saying in the end that field lines act like water. If you had a certain spigot or sprinkler sending out water in all directions and you put a tarp around that sprinkler, it doesn't matter what shape the tarp is. I mean, if it was a fully enclosing tarp, like a tent, right? If you put a tent around a sprinkler of water, it doesn't matter what shape the tent is. It doesn't matter what size the tent is. It doesn't matter where the sprinkler is within the tent, or it could be a number of sprinklers, doesn't matter where they are. It doesn't matter any sprinklers outside the tent. If you want to ask what's the total number of like the total amount of water at any given moment collected on the inside of the tent, it's fully determined by how many drops of water are coming out of the sprinkler at any given moment, right? Whatever water comes out of the sprinkler is water that will be grabbed by the tent. End of story. Because of the simple fact that no water droplet is ever going to be created or destroyed in the empty space between the sprinkler and the tent. You're only going to grab with the tent whatever water started with the sprinkler. That is literally what we're saying about field lines. That field lines are only created by points of charge. So as long as you know how many points of charge you have within an enclosure, then you know how many field lines are coming out of that enclosure. Okay, that's what the law is saying. In a way, it is that simple. But like all discoveries of physics, the simple is good. We're trying to discover truths that are so simple that it seems like maybe we always knew them anyway. But what we didn't know is how powerful they are for helping us to solve problems. So now we use this law, the top law, Gauss's law. We're going to use it to solve problems in physics, such as the ones on homework 7. And that's what I'm turning to now is homework 7. I'm continuing with homework 7, going over it. But I'm not doing it in the order. I'm just doing it in the order that I'm doing it. You'll have to like cross apply whatever I'm saying to the problems in homework 7. That's your job. So I'm not going in the order. Okay, I just said that. So let me just one thing I want to make clear. Okay. Okay. So I'm continuing through homework 7 now, right? And I'm gonna make, but I want to make two quick remarks, if I can make them quick. Two remarks. Oh, and good afternoon, people that, oh, I already said that. Two remarks. One, when I say solving problems, what, okay. First thing is, whenever I say solving problems, what I want to be clear is the kind of problems that we're solving always in the study of electrostatics is the problem is always given some amount of charge over here, some configuration, some shape of charge over here. What is the electrostatic field at some point in space over there? Every problem in electrostatics is given some bunch of charge, what's the field? And when we say what's the field, we don't mean what's a number usually. We mean what's a function. What is, like, can you give me a function that would tell me if I named a point in space, you could name what the field is? So what is E as a function of R? uh, um, at some displacement R from some bunch of charge over here. The reason it's always the same question, in other words, but the reason it's not always the same question is it from question to question, we're changing the way the charge is configured, is shaped. So it's like, what's the field due to a ball of charge? What's the field due to a cylinder of charge? What's the field due to a sheet of charge, etc. Okay, so to be clear before I go on, the question is still what is the field? The mechanism for solving or the technique for solving is thinking about flux. Okay, so I just want to emphasize that what all this flux stuff is becomes the useful way to calculate field. But field is still the goal. Flux is not the goal. It's a mechanism. Okay, that's comment number one. And comment number two. Well, I should really say this the other way around. I'll say it the other way around. Sorry. I mean, you could write it either way. Okay. Um, you essentially know this from chemistry or from other courses, but I have to just sort of remind you, because it mentions it throughout the homework 7. Materials can fall anywhere on a whole range between what we call, perfectly conducting versus perfectly insulating. Excuse me. What this means, what the difference is that insulating materials in perfectly insulating materials, all the net charge is stuck in place. Please note, and maybe even write down, notice I'm saying net charge. Like insulating materials such as glass or carbon or whatever, um, or wood, I guess, it could be charged or uncharged. Like no matter what, materials always have a bunch of protons and a bunch of electrons in them. But but when we say net charge, we mean an extra bunch of unpaired protons or unpaired electrons. Now, first thing to be clear is that I want you to be clear on is insulating material can be charged. And in fact, often is like in the original experiments of electrostatics and like Ben Franklin and stuff like that, we're rubbing glass rods with cat furs to make sparks and things. Like you definitely can charge up a glass rod. You can give it extra electrons, or you cannot. So it's not that, so to be insulated doesn't mean you can't be charged or you can't hold charge or anything. But what it does mean is that you hold the charge in place. The charge doesn't move around much. That's what insulating means. Conducting in conducting material, such as copper or gold or iron. In conducting material, metals usually. Um, and I mean electrically conducting, not thermally conducting. Like that's a related concept, but that is a different concept. In electrically conducting material, the electrons are free, as in they're not bound to the nuclei of atoms. They're not necessarily bound in molecules. They're literally free to wander around. And that means specifically free to follow the laws of physics, to follow F equals ma, i.e., uh, Okay, in conducting material, electrons follow the laws of physics, like they're free to, they're like hockey pucks on ice or something. So as long as there is a force acting on them, they're going to accelerate in that direction. Why would there be a force acting on any given electron? Because of an electrostatic field. Why would there be an electrostatic field? Because of all the other electrons. So if you put a bunch of extra electrons, if you put net charge on to conducting body, all the charges create field, and then all the charges are in that field. So all the charges start accelerating around. When they accelerate around, they move to different positions. So now they change the field lines. So now there's a different field, but there's still field. So now they move around again, et cetera, et cetera. So when you first, so with insulating material, wherever the charge is, it is. End of, for all intents and purposes, end of story. With conducting material, if it's net charge, and again, I should say with conducting material, it can be net charged or not net charged. Like that's not a distinction between insulating and conducting. Either one could be net charged. Once you net charge conducting material, once you drop a bunch of extra electrons, let's say, onto a piece of copper, then at first, all those electrons, like they're just like in random places, they create a big, very haphazard, intricate electrostatic field line pattern. So then all the electrons are in this field line pattern. So they start zipping around in accordance with the field lines, right? Each line represents an instantaneous acceleration vector for each of these charges. So now they all accelerate. Now they're all in a different spot. So now all the lines change. So then they accelerate again. So for a while, what I'm saying is when you first put a bunch of extra charges on a conducting body, you'll have all this statistical shuffling. I mean, I don't know any better way to put that. Like an arrangement, and then a new arrangement, and then a new arrangement. And I mean, it's not literally random. It's all following the rules of the fields. But if there's enough electrons there, it just looks like craziness. I would imagine. I've never like literally looked at an electron, but right, it's just craziness. Random configuration, random configuration, random configuration, random. But now here's the catch. Okay, so catch is with conductors, you add a bunch of extra charge to a conductor, it'll shuffle, 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 like the whole arrangement of all the charges, like wherever they are throughout the whole body of the thing will be here, then there, just shuffle, shuffle, shuffle. But if and when through this statistical shuffling, if and when all the charges ever happen to land in a configuration that cancels the field everywhere, then the shuffling would stop, right? Like, right? Like, if there is an arrangement that cancels the field, that makes E equals 0 throughout the body of the conductor, then there would be no more field. So there'd be no more forces on the charges. And so they would stop accelerating. So if they ever land in a configuration or Yeah, that cancels the field, then they'll stop shuffling. What is there such a configuration? Yes. If you take Gauss's law seriously, Gauss's law says that the number of field lines coming out of any closed surface is fully determined by the number or the amount of charge within that closed surface, right? So picture picture a big conducting, I mean, yeah, a big like block of gold or a big ball of copper or something like that, a big body of conducting material. If you take Gauss's law seriously, that means if you were to imagine a closed surface, a container, like right at the edge of that object. So, like if the thing is a big ball, if you imagine a sphere like right, an infinitesimally amount smaller than the radius of the given sphere, if you were to imagine a Gaussian surface right inside the surface of the object, according to Gauss's law, if there were no charge inside that closed surface, then there'd be no field lines fluxing out of that surface, right? So what it follows from there is if that if Q enclosed equals 0, then E equals 0, right? What I'm saying in English is imagine a block of gold, or well, imagine a block of anything where all of the charges are spread out uniformly throughout the surface of that object. I'm not saying how did they get, I'm just imagine that they are there. Imagine that all the charges are uniformly distributed throughout the surface of an object. Well, in plain English terms, if they're all spread out uniformly on the surface, that means they're all as far apart from one another as they could possibly be, if you really think about it, right? I mean, they're as far apart as the totality of them can be. If any one were any farther from another, it would be closer to the next one. If you see what I'm saying, it's like a max min, a maximization kind of situation. So the farthest away all the charges could be is if they were all on like the outer surface, assuming this is an isolated body, if they were all on the outer surface and they were all equally spread out through that outer surface, if they were all equally spread out through the outer surface, then first of all, just in English, they're as far apart from each other as could be. They're experiencing as little repulsion as you could imagine, right? They're minimizing the amount of repulsion. But now, in actual physics terms, they're canceling out like the field line from one with the field line of the next would be all the field lines would be canceling out, and we know throughout the body of the object, and we know this because if you imagined a Gaussian surface right with it right at the edge of this object, if you imagined a container there in your mind, it's not enclosing any charge, therefore there's no flux lines going through it. Like this is the power of Gauss's law. So I'm saying if so I'm saying uniform distribution of net charge throughout the surface of any body, like, any object, right, cancels E everywhere through the body, right? If charges, I mean, any object, I mean, this could even be true of an insulator, but I'm just saying any object for which all the charges are uniformly distributed throughout the surface of that object means there's no electric field within the object, right? That's Gauss's law right there. Therefore, what I'm saying, this is the part that always sort of blows my mind. Therefore, what I'm saying is with a conductor, if you let it go through, so with a conductor, that is a possible configuration, right? That is one of a bajillion different ways that the charges could be arranged through a conductor. So so you put a bunch of extra charges on a conductor and they start shuffling and shuffling, and they're everywhere, anywhere. Like they could be anywhere. A whole bunch of the charges could be inside the body of the thing, or they could all be grouped in a corner. They're shuffling, they're shuffling, they're shuffling. But one possible arrangement is this one. Is it a high probability arrangement? Absolutely not. It's the same low probability as any other arrangement you could consider. Like it's like a one chance out of all the different possible things it could do. It's a very low probability, but it does exist, right? Well, what I'm saying is, or what nature is saying, is that if you let the shuffling go on long enough, it will eventually accidentally land in this arrangement, right? It won't pursue it. It's not a high probability arrangement, but accidentally, statistically, it'll eventually happen. Say there's 52 million different ways, that all the electrons could be. And I'm not right. I mean, like, because electron one could be over here in this spot, electron two in this spot, or electron one could be here and electron two, right? So say you did a calculation, and this is called statistical mechanics. Like this is a thing. Say you did a calculation where you figured out the number of different ways all the charges could be configured throughout this body. Say there's 52 trillion. Well, one out of 52 trillion chance they're all going to land uniformly on the surface of that object. One out of 52 trillion times that'll happen. But if you let it shuffle for 3 quadrillion times, like if you let it shuffle long enough, it will eventually statistically fall into that arrangement. Like definitely no, but probably yes. So probably that if you really let it go a really long time, it's functionally definite from our point of view. Yes. Can we, right? I mean, this is, well, so, and can we do this with objects? Yes, because because electrons are so small. Every configuration that the electrons go through takes such a little amount of time that what I'm ultimately arguing is if you put a bunch of extra charge on a conducting body and you wait for a bajillion iterations, all you have to wait as a human being is like a few seconds or maybe a minute, maybe. And eventually, all those charges will find themselves accidentally in a uniform distribution throughout the surface of that body. And when they do, the shuffling stops, right? It's literally like saying it. Well, so let me complete. Uniform distribution of net charge throughout the surface of any body cancels E everywhere through the body. So I'm saying if a net charged conductor sits for sufficiently long time, eventually all charge. Oh, I don't know why it does that. Sorry. All net charge is found distributed uniformly through surface, and E is 0 through body. Let me make this totally clear. This is the real takeaway here, and I'm going to move on. But what I'm saying is, by this logic, from now on, you want to believe, like whenever anybody in a homework or on the web or in textbooks or in life, if someone's distinguishing between insulating material and conducting material in this electrostatic context, the distinction that they're getting at ultimately is if you have a conductor that's been sitting, well, and this is, If you have a conductor that's been sitting for a sufficiently long time, which probably just means minutes, I mean, at most, we call that a stable conductor. If the conductor has been sitting long enough, it has achieved stability, which means you've given it enough time for all the random shuffling to eventually lead to the charges being uniformly distributed throughout the surface of that conductor. And therefore, the field, the electrostatic field, is zero throughout the body of that conductor. If someone refers to a stable conductor, they are even if it's net charge, or especially if it's net charge, they are definitively telling you that all the charge is distributed uniformly throughout the surface of that conductor, and the field is zero everywhere through the conductor. And that happens in homework 7. Like, I'm giving away a big thing that, like, any question it asks you, because homework 7, it keeps saying, here's a situation. Now analyze it outside the situation, analyze it inside the situation. And then it says analyze it for an insulator, analyze it for a conductor. I'm telling you right now, because we still have 37 minutes, I'm going to do the hard problem for you right now, or one of the hard cases with an insulator right now, so you can see the math and everything. But whenever it's talking about a conductor, if you understand the logic of what I'm saying, then the answer for a conductor, the charge is always uniformly just, if it's a stable conductor, meaning a conductor that's been sitting around for a while, then the charge is uniform, the net charge is uniformly distributed throughout the surface, and the field is zero throughout the body. We know this of stable conductors. That's why we love stable conductors. 2 quick points on that. So it's like a big piece of knowledge, and it's coming from Gauss's law. But two things about that, and now I'm going to go on and solve problems, the harder problems with the insulators. One is the logic of this. I mean, you could see I never get tired of the logic is fascinating, because what we're not saying that conductors try to cancel fields. We're not saying that when we put charges into conducting bodies that they're trying to get to an arrangement that cancels a field. It's not a goal, and it's not a pursuit or something. It's total randomness. It's just statistical probability. In fact, and we're not saying, I mean, this is like a larger point about what stability means in science, or a steady state. We're not saying that there's any higher chance of achieving a steady state than any other state, but we're saying that a steady state, by definition, is steady. So that if you wait long enough, you accidentally fall in a steady state. Then what's special about the steady state is you won't change anymore, right? So this is literally, it's all literally like if I said to you, take a deck of cards and shuffle it, shuffle it, shuffle it. Just keep shuffling that deck of cards. But if and when you ever hit a situation where you get ace, 2, 3, 4, 5, through king, and then of the hearts, and then 8 through king in diamond. Like, once you get to a certain order of the cards, I want you to stop shuffling, right? Well, it's like very hard to reach that order. It'll take you a while. Like, there's nothing special. There's nothing that makes that order any easier to land on than any other. In fact, it's super hard when you think it through. But if you shuffled long enough, you would hit that order. And if the rule says that once you hit that order, stop shuffling, then that means as long as we wait long enough, we can always guarantee that by the time we come to you, we know what the order is going to be by the time we come to you, because once you hit it, you're not going to go to any other order, right? That's what stability means, especially in the electrostatic case. So stable conductors have all of their charge distributed uniformly throughout the volume, throughout the surface, and the field is uniformly zero throughout the body. Last point about that. That's what you might know. You've heard. So this is why it's like safe to be in a car in a lightning storm. It's not because of the tires being insulators. It's because the car is a conductor. And the minute the lightning hits the car, it'll distribute itself throughout the surface of the car. And the car is big enough, and the amount of charge would be a lot if it hit your body. But throughout the whole car, by the time it distributes itself uniformly, then the net charge, density is very small. Or that's what a lightning rod is, in life. Like, we take the charge and we bring it into the earth, which is a big conductor. So then the lightning, it's not like it disappears. It just gets distributed uniformly throughout the earth, the surface of the earth. So its effect on any one point on the Earth is tiny. So people call this a Faraday cage, or at least I call the car the Faraday cage. That's what's going on. All right. Now we have a half hour, we have 33 minutes. Let's do a problem from the homework. So we're going to see how we're going to use Gauss's law to compute the field at a certain location. And I'm going to do one example, but I'm going to show you the method of the example, and it's the same method for every example, whether it's in the homework or in life. Like it's one method, the Gauss's law method. I don't remember the example I'm doing now. I don't remember if it's one or two, like you'll figure that out, but consider an insulating sphere of radius r, net charge plus q. So we got a ball of charge, a big ball, a solid ball, like of glass or of carbon, but there's like a whole bunch of extra protons on it, right? And the ball is of radius, obviously I'm going to draw it in a second, but the ball is of radius r, it's got extra charge, positive q, and then it's an insulator. So we put wherever, so that means the charge could be anywhere, but wherever we decide to put it, it stays there. So we decide to distribute this charge uniformly through the volume, i.e., if we use the symbol rho, and this is what the homework did, if we use the symbol rho to mean amount of charge per unit volume, I'm sorry, I'm using the symbol tau to mean volume because we already use v for velocity and stuff like that. So often people use the lowercase symbol tau to mean volume. Sorry, just get used to it. If rho, and if the lowercase Greek letter rho stands for like three-dimensional charge density, amount of charge per unit volume, then we're assuming for this example, so that's triple equal sign. That's what rho means, charge per volume, right? Like mass per volume is mass density in chemistry. Charge per volume here would be charge density. But let's assume for this example that rho is a constant, that rho equals rho naught, meaning for this example, we're saying for any little volume you pick in this ball, like for any cubic centimeter you look at, you always find, say, 2 protons or whatever, well, two extra non-electrons, whatever, but 2 coulombs of net positive charge. We're saying for every cubic centimeter, there's the same amount of net charge. The density of charge is a constant. And again, I'm saying for this case, I'm not saying that always has to be that way. And in fact, it would never be that way in a stable conductor, right? In a stable conductor, it'd be zero throughout. But in an insulator, the charge can be wherever we want. So, and it stays there. So let's say we put it this way. We make plum pudding out of the charge. So then the picture would look like this. Right? There's like charge everywhere. So this is a ball of charge now. We've never done this before. I mean, everything we've talked about so far has been a point of charge or a point of charge. Now it's like a solid ball of charge. And right, and rho is a constant. And question asks us two cases. It asks us, well, all these questions ask us, what is the field, the electrostatic field function at a given point of space, given this arrangement? But it divides it into, well, really the problem in the homework is 4 cases. 2 cases for a conductor, which I'm going to let you do on your own. And I'm telling you right now, again, you'll get simple answers for the conductor. Everything I'm doing here, you'll do the same method, but it's going to be simpler for the conductor if you follow okay. But here, it asks for 2 cases. I mean, in all cases, the question is, what is E as a function of R at some location, right? But case one, the location is outside the sphere, and case two, the location is inside the sphere. In other words, case one, R is greater than R. In case two, and again, maybe in the homework it does it in a different order. I don't remember, but this is the way I'm doing it. So our question is, what's the field? And I'm going in this order. First, I'm going to figure out the field as a function of displacement at some location that's greater than the radius of this ball. And then I'm going to do the same calculation, but get a different result for some location within the body of the sphere. Okay. So the goal is to figure out field at a point. I'm telling you that the method is that we're going to think about it through Gauss's law and the concept of flux. Here is the method. Okay. It's kind of like that. So I'm about to give you literally like an algorithmic strict method. I'm not saying it's easy, but I'm saying it's a strict method that once you get it and you follow it, like it always works for Gauss's law problems. But to be as clear as I can be, I still believe in the 5-step method of solving problems. You still believe in it. You still want to do it on your final, et cetera, et cetera. So if you had a problem that was like a Gauss's law problem, you would still set it up like 5-step method. But then when you get to step 4, and start having to do the calculations, that's where I would divide step 4 into these following sub steps that I'm about to give you. Okay. So this is all like an expansion of step 4 specific to Gauss's law problems. So sub step 1, I hope that made sense. Stop me if that doesn't make sense. Okay. Sub step A, we'll call it, is draw the field line diagram. Always start with it. Just like with Newton's laws, we always start with a free body diagram. With electrostatics, you start with a free body. I mean, with a field line diagram. A diagram. Now, we haven't had a lot. I mean, that might seem intimidating at first, but remember all the rules that I gave you a couple weeks ago about how you draw a field line diagram and the whole. And you start with a scaling factor. I would, in my mind, when all other things are equal, I tend to always draw 8 lines for any 1 point of charge. That's like my scaling factor, just because it makes an asterisk, whatever. But then remember, the whole idea is you only start lines at positive, you only end them at negative. Other than that, they go on and come in from ever, right? They don't, right? And they can bend or curve, but they can't cross. And they're always the smoothest, simplest, most symmetric picture they could possibly be, given all those other rules, right? So field line pictures are simple. I mean, it's intimidating at first, but whatever the simplest way you could think of to follow all those rules is the way to make a field line picture. And the conclusion or the punchline that we were saying a couple weeks ago is field line diagrams are always an interplay of symmetry and asymmetry. They're going to be as symmetric as possible. They're only going to be as asymmetric as the thing that caused them, right? So like a dot, remember a dot has 0-dimensional asymmetry. It has no there's no particular axis that's treated as special by a dot. So things happen the same way in all directions. A dot, right? That's why all the field lines come out equally in all directions. Whereas like from a line, they come out in all directions except for the axis along which that line lies, right? Like it's always only as asymmetric as the thing that caused it. So we have here a ball. A ball is also it's like an expanded dot. I mean, it's 0-dimensional asymmetry. There is no axis of asymmetry for a ball. Unlike a line or a cylinder has one axis of asymmetry, or a plane has two axes of asymmetry. This does not. So I'm saying these field lines are going to look a heck of a lot like they do from a dot. I don't see any reason that they wouldn't be just like the ones from a dot. The only question in my mind is, and they will be, it's not a trick. It is that simple. The field lines will look just like they do for a dot. The only question is, in my mind, with 23 minutes left, is do they start at the center of this thing or do they start at the edge? Like those are the only two options I can think of that are both symmetric in all directions, right? And the answer, to cut straight to the chase, is if this were a conductor, if this were a conductor, hint, pro tip for the homework, then all the lines would start on the edge because there would be no field lines through the body of the conductor. All the charges would be on the edge if it were a stable conductor. But this is not, so that's what you do in the homework. But this is not a stable conductor. This is an insulator. The charge is everywhere. So there's field everywhere. So there's no reason that these lines are going to start at the edge. The lines start at the center like they would from a regular old dot. So the field lines from a sphere like this, or the field lines will look just like they would from a dot located at its center. So that's a field line picture, okay? Not a surprise, hopefully. And like anything else in this whole, really quickly, I feel like that, because this used to, I didn't know how my professors were drawing field line. Like I got used to them, but I just want you to know that the thing with drawing field line pictures is trust your instincts. The hard part about drawing field line pictures is you come up with something simple and you're like, I think that's too simple. Is that like, I don't really have confidence. If you come up with something, and if you're thinking, I think it's too simple, it probably isn't. It probably is right. But anyway, that's a field line picture of this. So that's step A. Now, sub-step B. Now, remember our goal. Our goal here is we want to know, at least for this case, we want to know what is the field right here. We want to know what, and that by that, I mean, what is a field function? What is E as a function of R right there at that dot? That's what I'm trying to figure out. But I'm going to do it by thinking about flux. And why? Because flux has this constancy associated with it. Well, you'll see why. But so what I'm going to do, sub-step B, I choose, this is like the big key part. I choose and draw a Gaussian, i.e. closed, surface at point P. But I choose one I choose a surface that will trivialize the integral, the flux integral. This is what I mean, and this is the key part. This right here is where we substitute physical thinking for mathematical computation. We have 20 minutes. Okay, what I'm saying is, well, I'm saying, first of all, we're going to choose and we're going to, in our minds, we're going to imagine some kind of surface, closed surface, like a container that contains the charge in the situation, right? And a container whose edge is like contains, or whose surface contains that point P. We're going to be picturing a container with a bunch of flux lines coming out of it and hope that somehow by capturing that point P, like if one of those flux lines goes through point P, we're going to be able to infer from the larger pattern of flux lines what's going on at P. So we're going to pick a container, a shape of a container that includes the point P. Now, the thing about Gauss's law is it says no matter what container we pick, no matter what shape, no matter what size, the flux, the number of lines through it is always going to be knowable and the same in advance. This is the power of Gauss's law. Any container we would pick would render Gauss's law true. I mean, Gauss's law will be true of any shape that we pick. But if we pick wisely, or therefore we can pick any one we want, and that gives us the freedom to pick a container that will trivialize our flux integral. What I mean by that is the integral looks hard to do, and it is hard to do, except whenever E comes out of the integral, as was the case last week, right? We did one flux calculation so far. It looked like it was going to be bad, or at least it looked that way to me. But then we finally got to the point where we realized all the stuff going on were all constants and they all came out, and all we were left was the integral of ds, which is just s. So as long as we pick a as long as we pick a shape, and this is the point of the integral, believe it or not, the reason we need to understand this flux integral is so that we never actually have to compute it. We have to understand it well enough to set things up to be able to get out of doing it. This is the Gaussian method. It's physics, not math, but you have to understand math to do it. I'm saying, so in other words, I'm saying we're going to choose and draw in our minds a surface for which, i.e., we're going to choose a surface for which E is a constant in magnitude and direction with respect to ds, where E does not change in magnitude or direction as you walk along that surface. As long as we, yeah, we're going to, okay. So now that sounds very complicated in a way, and sometimes it's not possible. Gauss's law is always true. It's not always helpful, but it's always helpful in these kind of problems. But what that means in English, what that ultimately means you're going to see here is we're going to choose a surface that mimics the symmetry of the original charge configuration. We're going to choose a surface that mimics the symmetry of whatever was, however the charge was arranged in the first place, whatever's causing the field lines. In other words, this all sounds very mathematically exotic, but at the end of the day, okay, so what I'm saying here in simple terms, I'm saying what we're going to do is at the point P, we're going to draw a sphere. The surface that we're going to consider is going to be the surface area of a sphere at point P. I mean, duh, like after all my talk, like it's like what you would think even if you didn't understand what I was saying. Now I'm not saying we always draw a sphere. Like if you had like later on in the homework where you have a line of charge, you're not going to draw a sphere. If you have a line of charge, you're going to draw a cylinder around the line because it mimics the symmetry. Like a line has one-dimensional asymmetry, a cylinder has one-dimensional asymmetry, or et cetera, et cetera. But here we have a globe, so we're going to draw a globe around it at the point P. So that's so it's 160. We have 14. So the blue, just to remember, the blue here is an actual ball of charge that you're imagining in the lab. Like you're imagining a glass globe or a carbon globe or a wood globe that has a whole bunch of protons all throughout it, like plum pudding. There's an actual ball that's charged up and uniformly charged up in the lab, and it's making field everywhere. That's what the red lines are. But now this yellow dotted circle is in your mind. We're imagining, we're considering a Gaussian closed surface containing our ball of charge. And the surface we're imagining is the surface area of a sphere that's at point P, i.e., oh, sorry. So choose, so here, here, choose sphere of radius lowercase r, like at P, like lowercase r, meaning wherever it is you're looking, that's the radius of this sphere. It's the variable. Capital R was the given size of the original ball of charge. Lowercase r is wherever is where the point P is, wherever we're looking. Okay, so that's substep B. So now substep C, inspect and verify. Is E really a constant in magnitude and direction? In other words, walk along, in your mind, walk along the surface. Does E change in mag or? So if I walk along this Gaussian surface in my mind, if I walk along the yellow surface, stepping from tile to tile, I'm asserting to you, but you want to think this through. And well, I'm asserting the same thing I asserted last week. Wherever I step, whatever tile I step on the yellow surface, no matter where I step, I think the field line, the red line, is hitting the tile perpendicular to the tile, right? The surface area of a globe is always fully perpendicular to the radii of the globe at that point. So wherever I'm stepping, I don't think the angle is ever changing. It's always full on flux, fully perpendicular. And wherever I'm stepping, the density of lines is not changing, right? I mean, they're spreading out uniformly from a point, zero dimensionally asymmetrically, with zero dimensional asymmetry, right? So if I think, in other words, you'll know you understand what I'm saying if you think of the counter examples. Like if I had drawn a box, like a cube, Gauss's law would still be true, but it would not be the case that E would be a constant throughout the S of that box. Like some places, the field lines would be hitting corners. Some places the field lines would be hitting dead on 90 degrees. Some places the field lines would be hitting at weird angles in between 0 and 90 degrees. And the density of the field lines would be a lot bigger, like at corners than and vice versa. So the field would not be constant throughout a cube. Does that mean Gauss's law is wrong? No, but it means that I would have to do a really hard integral to use Gauss's law, and at that point it's not worth it. In this case, I've drawn something for which E is a constant. Therefore, I'm verified. I mean, in my mind, I think yes. Yes. E is constant in magnitude and direction with respect to ds. Okay, it's 120. I'm not saying E is a universal constant. Like the field strength is getting weaker and weaker as you get farther and farther away from the center of that ball. Like the field is weakening, but it's not weakening as a function of ds. It's not weakening as you walk around a given surface. It's only weakening when you walk from one surface to another. Okay, so we picked the right surface. We picked a constant E surface. So substep 4, write down Gauss's law, literally now. Here's Gauss's law. And I'm telling you, you want to write it down every time. Okay. And then substep 5, take out E every time. If you've done this correctly, you will take out the E and solve both sides. I'll show you, and that's what we're going to do right now. Every time, if you've done it correctly, you will, well, here, every time this will turn into this every time. But if you ask, why can't I just start with this then? Because you only know how to get to this step once you've chosen your particular surface. And you're going to need to know what that surface is in order to now expand both sides. Watch. 122. So we're almost E integral of ds means E times the total surface area. All equals charge enclosed by that surface area over epsilon naught. Well, the total surface area of the surface we chose a sphere at radius lowercase r. So the total surface area is 4 pi. I mean, this looks very familiar, right? 4 pi lowercase r squared. The charge enclosed is just the total. I mean, we're outside the sphere. So we enclosed all of that given charge, which was told to us in the problem to be called positive capital Q. So we enclosed all of it in our sphere. And then there's space, we are at a big sphere out here. The ball of charge is here. So there's like a bunch of plus Q. And then there's like empty space, but I don't care because the whole point of Gauss's law is just whatever you've enclosed is what determines the flux. Doesn't matter where it is. Doesn't matter if there's gaps, right? So E equals that. And then now the point, so we've said because we knew the flux was going to be Q over epsilon naught no matter what. And then because we chose, like, no matter what the shape is, then we chose a good shape to make the integral trivial. Now we've turned the flux calculation into a field calculation because now we just divide both sides always. Divide both sides. And what we have is E equals 1 over 4 pi epsilon naught Q over R squared. And that's the magnitude. And the direction of the field is clear from our field line picture. It's radiating out. So this is the answer to this case. Now we have 6 minutes, perfect. This is the answer to this case. I'll very quickly say, you might think we just went in a big circle. If you're with me, you'll recognize that answer. You've seen that before. That looks like just the answer from Coulomb's law. It is, but it's a discovery nonetheless. Like, it doesn't mean we just wasted our time. What we've just concluded is that if you're outside a big ball, the field due to that big ball is exactly equivalent to the field from a point. You might have already guessed that, or it might make sense once I say it that way. It is a discovery. Like, we just added up the fields from all of the little points that comprise a ball. But because they all made something that has the same symmetry as a point, because they just made a shape that has the exact same field lines as a point, if you're outside that ball, the ball is acting just like a point as far as you're concerned, especially if you're really far away. It probably just looks like a point. This is why, like in the case of gravity, all the gravity from the entire planet Earth, we always act like it's just gravity just coming from a dot at the center of the Earth. Because as long as you're outside a sphere acts like a point located at its center. That's what that result says. Okay, so it's not redundant. I mean, it's knowledge, but we've just decided that the field outside the insulating sphere is equivalent to the field outside a point. However, with 5 minutes left, what if we go inside? Okay, this is trickier and more interesting, but we can do it fast because we've done most of the problem already. So now case two. Case two, what if R is less than capital R? Like, what if we're inside? Okay, same Gaussian procedure. Same procedure. First, draw the field line. So, okay, but we've drawn the field lines. It's the same field line picture as before. Substep two, choose and draw a Gaussian surface. Again, it's going to be a sphere. We're mimicking the symmetry of the charge configuration. So it's going to be a sphere again, only now it's going to be at that P2 inside. So we're going to draw a sphere inside. Inspect and verify. Yes, it works. So then write down the law and solve. Okay, so it's all the same as outside. Only catches this. Only catches this. Too bad someone just left because this is, well, anyway. Again, it's this. It's going to be a different answer in case people are leaving because they think it's going to be this, just like before. And if I do it all out, it's going to be this, just like before. The only catch now, though, is the charge that we enclose now is not all of the Q. We can't just substitute in capital Q because we're inside that ball. We're only enclose our shape, our surface is only enclosing a portion of that ball. How much of a portion? I don't know, but I know that rho is a constant. In other words, I know that the charge enclosed in some volume must be the same ratio as the total charge per the total volume, right? Like that's the key. The density is a constant. So I have this, I'm just rewriting it. We're almost done. I'm just solving for Q enclosed right now is what I'm doing. So that means Q enclosed over the volume of a sphere. The volume of a sphere is the integral of the surface area of a sphere, not coincidentally, right? So is that, and the total volume is 4/3 pi given r cubed, right? So the 4/3 and the pi's cancel. And what we're saying is that the charge enclosed equals this, meaning it's some fraction of the total charge. How much of a fraction depends on how far out you are. If since volume is three-dimensional, if you go out to half the radius, you will enclose 1/8 of the total charge. That's what that says. So I plug that back in. E times 4 pi r squared equals q r third over r third over epsilon naught. I'm just plugging it in for charge enclosed. So these r's cancel, and we're left with this different answer from before. We've got 2 minutes left. I'm saying that the field function I'm saying with 1 minute left, I'm saying that r cubed in the denominator, that's a constant. That's just a number. But the lowercase r in the top, that's the variable. This is saying that the field gets stronger and stronger as you walk out from the center. It's saying right at the center of this whole thing, there's no field at all. R equals 0, E equals 0. As you walk out from the center, the field gets stronger and stronger, directly proportional to where you are. So, right. And then when you get to the surface, and go outside, then it drops off and gets weaker and weaker. This is saying inside the ball, even though you're getting farther and farther away from the center, you're in effect standing on a bigger and bigger ball of charge. This is exactly correct. And it's 1:30, so we'll just leave it at that. Have a nice weekend. We'll pick up on this.
Bye, Professor.
Bye. Oh, thank you. Thank you. Bye. Thank you. Yes, have a nice day. Awesome.